Picture a wall with two narrow slits cut into it, and beyond the wall, a screen. Now picture firing a single particle at that wall. One electron, so small and so alone that there is nothing else inside the machine with it. It leaves the source, crosses the gap, and strikes the screen, leaving a single dot. You fire another dot. For a while, the dots fall like scattered rain, random and meaningless. And then, slowly, out of thousands of separate impacts, something appears that should not be there. Bands of light and dark, ordered and precise, the unmistakable fingerprint of a wave. But you did not send a wave. You sent them one at a time, each particle alone, with nothing else to interfere with. And yet each electron, it turns out, had somehow passed through both slits at once and interfered with itself on the way to the screen. This is the most famous experiment in physics, and after more than 200 years, the people who understand it best will tell you, without embarrassment, that they do not really understand it at all. The physicist Richard Feynman called it the only mystery. He meant that almost everything strange about the quantum world is hiding inside this one simple setup. But the strangest part is not the pattern. The strangest part is what happens when you try to catch the particle in the act. Place a detector at the slits to see which one each electron actually goes through, and the pattern vanishes. The wave behavior disappears. The particles go back to behaving like ordinary specks. The experiment does one thing when no one is checking, and a different thing when someone is. Physics has tested what happens when nobody is watching, and the results do not add up. Let us begin. The story starts with light, and with a quiet English polymath named Thomas Young. In 1801, the question of what light was had not been settled. Isaac Newton had argued that light was a stream of tiny particles, and Newton was not a man people enjoyed contradicting. Young cut two thin slits in a barrier and let sunlight pass through them onto a surface beyond. If light were particles, he should have seen two bright lines, one behind each slit. He did not. He saw a series of bright and dark bands spread across the surface. Bands like that have only one explanation. The light was travelling as a wave, passing through both slits at once, and where the crests of the two waves met, they reinforced into brightness, and where a crest met a trough, they cancelled into dark. It was the same thing that happens when you drop two stones into a still pond and watch the ripples cross. Young had shown that light is a wave. For 100 years, that seemed to be the end of it. It was not the end of it, because light, we would later learn, is also made of particles, and matter, we would learn, is also made of waves. In 1961, a physicist named Klaus Janssen at the University of Tübingen in Germany did Young's experiment again, but he did not use light. He used electrons. Electrons are matter. They are tiny pieces of the same stuff your body is built from, and everyone agreed they were particles, hard little specks with mass and charge. Janssen fired a beam of them at a barrier with slits, and on the far side he found the same thing Young had found with light: bands, an interference pattern. The electrons, somehow, were behaving as waves. A skeptic could still escape the full strangeness of this. A beam contains an enormous number of electrons, all flying together. Perhaps, the skeptic might say, the electrons were simply bouncing off one another, jostling in flight, and the pattern was some accident of the crowd. To kill that idea, you would have to send the electrons one at a time, one alone in the machine, then the next, each with no companion to bump into. For decades, this was considered too difficult to do, a pure thought experiment. Then the technology caught up. In 1974, a team in Bologna, Italy, working with Giulio Pozzi, recorded single electrons building a pattern. And in 1989, Akira Tonomura and his colleagues at the Hitachi Research Laboratory in Japan did it so cleanly that they filmed it. They released electrons one by one, slow enough that only a single electron was ever crossing the apparatus at any moment, and they recorded where each one landed. What the film shows is one of the eeriest sights in science. At first, single dots, scattered, with no order at all. The screen looks like random noise. You could watch for a long time and swear there was no pattern there. And then, As the dots accumulate into the thousands, the bands emerge from the chaos, sharp and certain. It has been called the most beautiful experiment in physics. Each electron arrived alone, as a single dot, a particle, but the population of dots arranged itself into the interference pattern of a wave. Every individual electron, with nothing else in the machine, had gone through both slits and interfered with itself. In 2013, a group led by Herman Batalan at the University of Nebraska closed the last gap, building a true double slit they could open and shut one slit at a time, confirming every piece of Feynman's old thought experiment exactly as he had imagined it. So this is the settled, repeated, unquestioned fact at the center of everything that follows. A single particle sent toward two openings does not go through one or the other. It goes through both as a spread-out wave of possibility, and only becomes a single definite speck when it strikes the screen and is recorded. And it would be a comfort to believe this is a quirk of things too small to matter. It is not. The same experiment has been carried out with whole atoms, and then with molecules, and the molecules have only gotten bigger. In 1999, Marcus Arndt and his colleagues at the University of Vienna sent buckyballs through the slits, soccer ball-shaped molecules made of 60 carbon atoms each, objects you could almost imagine seeing. They interfered with themselves, just like the electrons. Each one passed through both slits at once. In the years since, the experiment has been pushed to molecules of thousands of atoms. There is no known size at which the strangeness switches off. The line where the quantum world ends and the ordinary world begins has never been found. As far as anyone can prove, it may not exist. Now we arrive at the part that has unsettled physicists for a century. It is a simple, obvious question. If each electron really goes through both slits, then surely we can prove it. Let us just look. Let us place a small detector at the slits, a device that registers which slit each electron passes through, and watch it happen. So they did. And the moment the detector is switched on, the moment the path of each electron is actually recorded, the interference pattern collapses. The bands vanish. What appears on the screen instead is two simple clumps, exactly what you would expect from ordinary particles that went through one slit or the other, like throwing tennis balls through two windows. The wave is gone. Each electron now goes through a single slit, like a normal object, and behaves itself completely. Switch the detector off and stop recording the path, and the wave comes back. The bands return. Run it again with the detector on, and they disappear again. You can do this as many times as you like. The result never changes. When the path the particle took is recorded, the particle behaves like a particle. When the path is left unrecorded, the particle behaves like a wave that took every path at once. Sit with how strange that is. Nothing about the slits changed. Nothing about the electrons changed. The source fired them the same way, at the same speed, toward the same two openings. The only thing that changed, between a universe of waves and a universe of specks, was whether the information about which path each particle took existed somewhere. Not the force applied to the particle, not the energy, the knowledge. It is as if reality checks whether anyone could find out what it did, and chooses how to behave based on the answer. This is where the easy assumptions begin to fail, and where most explanations you have heard go quietly wrong. Because the obvious way to describe what I have just told you is to say that the electron knew it was being watched, that it sensed the observer and changed its behavior, shy and self-conscious, like a person who acts differently when a camera is pointed at them. That is the version in 1,000 documentaries, narrated in a hushed and meaningful voice. The particle knows you are looking. It is a beautiful story, and it is wrong. Or at least, it is hiding the real question behind a word that does too much work. The word is watching. Because the next thing physicists had to figure out was what watching actually means. Does the universe care that a conscious mind has come to know the answer? Does it require a person at all? Or is something far colder and stranger going on? Something that would happen in an empty laboratory with no one in the building, simply because a single particle left a mark that could, in principle, be read. the answer turns out to be the most important part of the whole story, and it is where we go next. The easy answers fail first. They always do. We ended on a single word, and the word was watching. When the path of a particle is recorded, it behaves like a particle. When the path goes unrecorded, it spreads out like a wave and travels every route at once. So the obvious question is the one a child would ask. Watched by whom? Watched how? What exactly does the universe count as looking? There are three easy answers. Each one is satisfying, each one is wrong. And the way they fail, one after another, is the whole reason this old experiment still keeps physicists awake at night. The first easy answer is the most physical, and for a long time it was the textbook explanation. It says there is no real mystery here, only clumsiness. To detect which slit an electron goes through, you have to do something to it. You have to bounce a photon off it, or push it through a field, and that interaction gives the electron a tiny kick. The kick nudges it off course, and if you disturb the particle enough to learn its path, you have disturbed it enough to smear out the delicate pattern. No spooky knowledge required, just a clumsy microscope bumping into the thing it is trying to see. It is a good answer. Werner Heisenberg himself reached for a version of it, and it is not entirely wrong, because measuring a quantum system really does disturb it. But it cannot be the whole story, and here is how we know. Physicists learn to build witch path markers so gentle that the kick they give the particle is negligible, far too small to wash out the pattern by force. They can tag the path while barely touching the electron at all, and the interference still dies every time. The instant the witch path information becomes available, even through the lightest possible touch, the wave is gone. So it was never really about the force of the bump. The disturbance was a distraction. What kills the wave is not how hard you hit the particle. It is whether the universe ends up holding a record of where it went. Which leads straight to the second easy answer, and this is the famous one, the seductive one. If it is not about force, if it is about a record, then maybe knowledge itself is the point. Maybe it is consciousness. Maybe the act of a mind coming to know the result is what reaches in and collapses the wave. This is the version that launched 1,000 late-night conversations and a small industry of books claiming that your mind creates reality, that the universe needs a conscious observer in order to exist, that you are the magician and the cosmos is your trick. It is a wonderful story. It is also, as far as the physics can tell, simply false. And the experiments are not subtle about it. The detector at the slit does its work, whether or not a human being ever looks at the readout. You can record the witch path information onto a hard drive, seal it in a box, and never read it. The interference is gone just the same. You can have the data automatically deleted before any person could ever see it. The wave does not come back to reward your ignorance. Researchers have gone further and tested directly whether human attention itself, a person simply staring at the apparatus, changes the outcome. It does not. The quantum statistics do not care whether you are paying attention. A photodetector does not wait for a graduate student to glance over before it functions. The universe does not need your eyes. What it needs is something called decoherence, and this is the real heart of the matter, the thing the mystics get exactly backwards. When a particle in a superposition interacts with something large and messy, a detector, a stray photon, a single molecule of air, anything that carries off a trace of which path it took, the particle becomes entangled with that environment. Its delicate wave of possibilities is stirred into the vast and chaotic state of everything around it, and the interference, while not technically erased, becomes impossible to ever gather back. The information has leaked irreversibly into the world. The physicists who worked this out, Heinz-Dieter Zeh in 1970, and later Wojciech Zurek, showed that you do not need a conscious mind anywhere in the picture. You need only an interaction that spreads the record into the environment and cannot be undone. The observer was never a person. The observer is the rest of the universe. Which brings us to the third easy answer, the strangest one, the one that sounds like science fiction and gets repeated as though it were settled fact. If the universe only commits when the path is recorded, then what happens if we wait? What if we let the particle pass the slits, let it fly almost all the way to the screen, and only then, at the last possible instant, decide whether to record its path? Could a choice made now reach backward and change what the particle already did, before the choice was made? John Wheeler, the Princeton physicist, dreamed up exactly this experiment in 1978 and called it the delayed choice. For 3 decades it was only a thought. Then, in 2007, a team led by Vincent Jacques in Paris actually built it, and the result was as advertised. When the path was recorded, even though the decision came after the particle had already passed the slits, it had behaved like a particle all along. When the path was not recorded, it had behaved like a wave all along. A more elaborate version, the quantum eraser, first run by Yoon Ho Kim and his colleagues at the University of Maryland in 1999, went further still. It let you record the path, destroying the interference, and then erase that record afterward. And when you erased it, the interference returned. The path was measured, the pattern died, the record was wiped, the pattern came back, after the fact. You can see why people lost their minds over this. It looks exactly like the present reaching back to rewrite the past. It is described that way in countless videos and articles, but it is not what is happening, and the physicists who built these experiments have spent years trying to say so plainly. There is no signal travelling backward in time. The trick is hidden in how the results are sorted. In the eraser, the full set of particles that strike the screen shows no interference pattern at all, ever. The pattern only emerges when you take that complete, smeared-out blur and sort it into groups according to a second measurement made on a partner particle. Inside one group, an interference pattern is hiding. Inside another, its mirror image hides. Add all the groups back together, and they wash out into the same featureless blur you started with. Nothing about the past changed. You only discovered, after the fact, how to file data that had been sitting there all along. As the physicist Sean Carroll and others have said bluntly, the mystery is real, but time travel is not the explanation. The easy answer fails, like the two before it. So where does that leave us? We have ruled out the clumsy bump. We have ruled out the conscious mind. We have ruled out the rewritten past. Strip away the 3 comfortable stories, and what remains is the actual problem, the one with no agreed solution to this day. It is called the measurement problem, and it is the deepest unsolved puzzle in all of physics. Here is its shape. Quantum theory comes with a piece of mathematics, the Schrödinger equation, that describes how a system changes over time. It is precise, it is smooth, and the theory it belongs to has been tested to an accuracy matched by almost nothing else in science. And that equation says systems stay in superposition. Left undisturbed, the electron remains a spread-out wave of both paths at once. The equation never, on its own, picks one. It contains no step in which the wave collapses to a single outcome. And yet every time we actually look, we find one outcome. One dot, one slit, one definite world. The mathematics describes a reality of endless overlapping possibilities. Our experience delivers a reality of single, solid facts. And nobody can fully explain how you get from the first to the second. Decoherence, the leaking of information into the environment, tells us why we stop seeing the overlapping possibilities. It explains why the blur becomes impossible to detect, but it does not explain why we end up seeing this outcome rather than that one. It accounts for the disappearance of the interference. It does not account for the appearance of the single result. That final step, from many possibilities down to one actual fact, is exactly the part the equations leave out. And the most honest physicists will tell you plainly that we do not know what fills the gap. Erwin Schrödinger saw the absurdity of this as early as 1935 and built a little nightmare to make the point. Put a cat in a sealed box, he said, with a single radioactive atom and a vial of poison rigged to shatter if the atom decays. The atom, being a quantum object, enters a superposition of decayed and not decayed. And if the atom is in both states at once, then the equation says the cat, chained to the atom's fate, is in both states at once as well, alive and dead, together, until the box is opened. Schrödinger did not offer this because he believed in undead cats. He offered it to show that something is missing from the theory. Somewhere between a single atom and a living animal, the rule that lets a thing be in 2 states at once has to stop applying. But the mathematics draws no line. It never says where the quantum world ends and the solid one begins. We saw in the last chapter that the experiment already works on molecules of thousands of atoms. No one has found the ceiling. The line may not be there at all. And if you still imagine measurement as something gentle, a passive reading of what was already there, the universe has one last surprise. Measurement can reach in and physically change what a system does. It can even hold it still. In 1977, two physicists at the University of Texas, Baidyanath Misra and George Sudarshan, predicted something they named after Zeno, the ancient Greek who argued that an arrow, observed at any single instant, is motionless and so could never move at all. Their quantum version went like this. Take an unstable particle, one fated to decay, to change from one state into another on some schedule. Leave it alone and it decays on time. But measure it over and over, quickly enough, and the decay slows. Measure it continuously and it stops. The particle freezes in its original state and refuses to change, not because you touched it, but because you kept asking. In 1990, Wayne Itano and his colleagues at the National Institute of Standards and Technology built it for real, with beryllium ions poised to jump from one energy state to another. The more often they checked, the less the ions changed. At the highest rate of measurement, the jump was almost entirely frozen. A watched quantum pot, it turns out, really does refuse to boil. Read that back slowly. By doing nothing but look, again and again, you can pin a piece of the universe in place and stop it from evolving at all. Observation here is not a camera quietly recording a scene that would have happened anyway. It is a hand laid on the world. So we are left with more than we bargained for, and less. We do not know what counts as a measurement. We do not know why looking delivers a single outcome when the mathematics insists on all of them. We do not know where, between an atom and a cat, the strange rules are meant to surrender to the ordinary ones. We do not even know for certain that they ever truly do. What we do know is small and exact and impossible to escape. A particle whose path goes unrecorded explores every possibility at once. The instant the universe takes down a record of what it did, the possibilities narrow to one. And no amount of cleverness has yet found the seam where that change is stitched. But everything so far has concerned a single particle, alone, facing its two slits. One object, choosing between two paths. The truly disturbing part of this story begins when you take two particles, bind them together, and send them to opposite ends of the world. Because then the question of what happens when you look at one of them stops being about a speck in a laboratory. It becomes a question about whether distance is real at all. And that is where this story goes next. Take two particles and make them together in a single event from a single source. Born as a pair, they can be created in what physicists call an entangled state, their properties bound up with one another so completely that neither particle has a definite value of its own. Now carry them apart, one to your left hand, one to your right, one to this room, one to the next city, one, if you like, to the far side of the galaxy. Then measure one of them. The instant you do, it settles into a definite value, and in that same instant, its distant partner settles too, into the exactly matching value, as though it had been told. Not a moment later, not after a signal could have crossed the space between them. Instantly, no matter how far apart they have been carried. Albert Einstein hated this. In 1935, together with Boris Podolsky and Nathan Rosen, he laid the problem out in a famous paper and refused to accept what it seemed to imply. He called it spooky action at a distance, and he was certain it could not be the final truth. There had to be an ordinary explanation, he argued. The particles must simply carry hidden instructions written into them at the moment of their birth, like two sealed envelopes mailed to opposite cities, each already containing its answer. Open the one in your hand and you instantly know what the other holds, not because of any spooky link across the void, but because the answer was sealed inside both from the start. No magic, just information you did not happen to have until you looked. It is a completely reasonable idea. If it were right, the strangeness would drain out of the experiment, and quantum mechanics would be nothing but ordinary ignorance dressed up in mathematics. And for 30 years, nobody could tell whether Einstein was right, because both pictures predicted exactly the same results. It looked like a question for philosophers, not physicists, one no experiment could ever settle. Then a single man sat down with a pencil and made it answerable. His name was John Bell, and in 1964, working at CERN, the great European physics laboratory, he did something no one had believed possible. He found a way to tell the two pictures apart. Bell proved, on paper, that if the particles really did carry hidden instructions written at birth, and if no influence between them could travel faster than light, then the agreement between their measurements could only ever be so strong, and no stronger. There was a ceiling, a hard mathematical limit, known ever since as Bell's inequality. And quantum mechanics predicted results that broke straight through that ceiling. The two pictures no longer matched. They produced different numbers, and numbers can be measured. This was the turning point. A question that had seemed purely philosophical, about the deepest nature of what is real, had become an experiment you could run on a bench. Someone only had to build it. They built it. In 1972, John Clauser, working in California, ran the first real version, and the results sided with quantum mechanics and against Einstein. The correlations were too strong. They broke the ceiling. But the early experiments had gaps, small loopholes, ways the universe might still be hiding ordinary instructions. So the experiments got better. In the early 1980s, Alain Aspect in France closed one of the most important gaps, switching his measurement settings so quickly while the particles were already in flight that no signal moving at the speed of light could have reached across to coordinate them. Anton Zeilinger in Vienna pushed further still, even using the light of distant stars to choose the settings. And in 2015, several teams at once, led first by Ronald Hansen at Delft in the Netherlands, finally closed every major loophole at the same time. The verdict was absolute. Einstein's sealed envelopes do not exist. The particles do not carry pre-written answers. In 2022, Aspect, Clauser and Zeilinger were awarded the Nobel Prize in Physics for proving it. So sit with what was proven, because it is one of the strangest certainties in science. The world cannot be both local, meaning nothing here influences anything there faster than light, and definite, meaning things possess real values before anyone measures them. At least one of those comforts has to go. Either the particles have no definite properties until the moment they are measured, the haze of possibility from the double slit reaching all the way up into the large world, or the two particles remain a single connected thing, no matter how far apart you carry them, so that the distance between them is, at some level, not real. Perhaps both. But there is no version of the story left in which two genuinely separate objects quietly carried their matching answers the whole time. I have to be honest about one thing here, because it is exactly where many tellings go too far. None of this lets you send a message faster than light. When you measure your particle, the result looks completely random, and so does your partner's. Neither of you can control the outcome, so neither can use it to signal the other. The connection is real, but it is shy. It reveals itself only afterward, when you compare your records over an ordinary channel, slower than light, and find that your random-looking results agreed all along. The universe guards this rule carefully. It will be as strange as it pleases. It will not let you break cause and effect. And this is the part that should matter to anyone who has ever looked up at the night sky, because these experiments never stayed on a laboratory bench. Physicists have wired them to the universe itself. One lingering doubt in the Bell tests was that the equipment choosing the measurement settings might somehow be coordinated in advance, quietly faking the result. To rule that out, you would want the choice made by something utterly disconnected from the experiment. So in 2018, a team including David Kaiser at the Massachusetts Institute of Technology, working with Anton Zeilinger, reached for the most disconnected things in all of creation: quasars, the blazing cores of distant galaxies whose light has crossed space toward us for billions of years. They used the light of two quasars, one of them more than 12 billion light-years away, to choose their detector settings. The decision about what to measure had, in effect, been made by photons that left those galaxies before the Sun, the Earth, or a single atom of your body existed. And still the correlations held. Still Einstein's hidden instructions failed. John Wheeler had foreseen this, imagining the delayed choice experiment stretched across the heavens. Let the light of a distant quasar pass on both sides of a galaxy, lying between us and it. The galaxy's gravity bending that light around itself like a lens, so the light travels for billions of years, taking both routes at once. Only as it finally arrives do we choose how to look, whether to ask which way it came, or to let the two paths interfere. The choice we make tonight appears to reach back across nearly the whole age of the universe and settle what that ancient light did long before we were born. The honest physics, as always, forbids any real message to the past. But the experiment that began with a wall and two slits has now been carried out with the observable cosmos as its apparatus, and it gives the same impossible answer. And then, in just the last few years, the question turned inward, onto the observer itself. We have treated measurement as the thing that makes reality definite. But what is a measurement except one part of the universe coming to hold a record about another part? And if that is all it is, nothing stops us from asking the next dizzying question. What if we place one observer inside the experiment and a second outside it, watching the first? This is an old puzzle, first imagined by the physicist Eugene Wigner. Picture a friend, sealed inside a perfectly isolated laboratory, who measures a quantum particle and gets a definite result. To the friend, the matter is closed. The particle was here, the needle pointed there, a fact was recorded. But now picture Wigner standing outside that sealed lab, describing the whole thing, friend included, with the equations of quantum mechanics. From the outside, the friend and particle together are just one more isolated quantum system, perfectly entitled to sit in a superposition, with no definite outcome yet at all. The friend within is certain a fact exists. Wigner without is equally certain it does not. Two observers, two accounts of the same event that cannot both be written into one story. For decades this remained a paradox on paper. Then, in 2019, a team led by Massimiliano Proietti and Alessandro Fedrizzi at Heriot-Watt University in Scotland found a way to test a version of it. Using 6 entangled photons, they built a miniature Wigner's friend scenario with stand-in observers inside and out, and checked whether the two observers' facts could always be reconciled. The results broke the limit that a world of shared, observer-independent facts would have to obey, and broke it by 5 standard deviations. The very next year, a separate group proved an even stronger version. Under a few reasonable assumptions, the experiments say, there is no single set of facts that every observer must agree upon. What is settled and real for one observer need not be settled and real for another. Now I want to be careful here, more careful than most tellings are. The friend inside the box in these experiments was not a conscious human being. It was a single photon, standing in for an observer. No person has been split into 2 contradictory realities, and nothing here proves that objective reality is a comforting illusion. What the result does is sharper and more troubling. It says that a small handful of assumptions we would all dearly love to keep, that the world is local, that an experimenter is free to choose what to measure, and that once an observation is recorded, it becomes a fact for everyone, cannot all be true together. One of them, at least, has to give way. The universe is telling us we cannot keep every reasonable thing we want, and a century in, no one can agree on which. Which brings us back, at last, to the question we began with, the one printed on the screen before any of this started. What happens when nobody is watching? After everything, here is the honest answer, and it is not the one the mystics are selling. When nobody is watching, a particle is genuinely everywhere it could be, doing everything it could do, all at once. But the watching was never about you. It was never about a mind, or attention, or awareness. The thing that turns a haze of possibility into a single hard fact is not a conscious observer. It is information. The moment the universe anywhere takes down an irreversible record of what a particle did, a detector clicking, a molecule of air scattering off it, a single photon carrying away the news, the possibilities narrow to one. Watching never needed a watcher. It needed only a record. When we asked what happens when nobody is watching, what the universe heard was, when nothing is recorded. And when nothing is recorded, nothing is yet decided. And the results do not add up. Not because the mathematics is broken. The mathematics is the most precise and successful description of nature that human beings have ever produced. The quiet engine behind every transistor and laser and glowing screen you have ever held. The results do not add up because that flawless mathematics describes a reality nothing like the solid, single, observer-independent world we were all so certain we lived in. A reality in which things hold no definite state until they are measured. In which two objects on opposite sides of a galaxy can be one connected thing. In which two observers can carry contradictory facts and neither one is wrong. 100 years on, with the most accurate theory in the history of science in our hands, we still cannot say what a measurement is, or why the simple act of recording turns the whole shimmering field of maybe into a single, stubborn, irreversible yes. Somewhere right now, in a dark laboratory, a single electron is leaving a source and drifting toward a wall with two slits cut into it. No one is in the room. No detector is switched on. Nothing, anywhere, is keeping a record of which way it goes. And so it goes both ways. It is not a speck following a hidden path. It is a wave of pure possibility, passing through both openings at once, spread across the gap, waiting. The banded pattern on the screen beyond is already implied within it, faint and certain, the same fingerprint that has unsettled physicists for more than 200 years. It will stay that way, undecided, everywhere at once, for exactly as long as the universe keeps no record of it. The instant anything does, it will become one thing, in one place, with one history, as though it had never been anything else. And we still do not know what counts as that instant. We do not know where the line falls, or whether there is a line at all. We know only that the world we see, solid and single and sure, is built entirely out of moments like this one. Out of haze quietly becoming fact, for reasons no one has ever been able to name. The electron drifts toward the slits. Nobody is watching. And so, for now, it is everything at once.